In this video, I'm going to kind of introduce the idea behind the computation formula, and I'm going to do that by actually calculating the standard deviation for this particular data set. And we're going to see, because the mean doesn't come out evenly, that it takes a lot more work to calculate the standard deviation. It's just a little more tedious. And then I'm going to show you how you can use the computation formula to do it. And we'll be looking at that in the next video. So we're just going to calculate the standard deviation just like we did using the definition formula, just like we did in the previous videos. So in this case, n is 6, and now I got to calculate my mean. And so let's see here. I got 9 plus 3 plus 5 plus 1 plus 6 plus 4. And that's like 28 divided by 6. And what we're going to find here is I get like 4.6 repeating. And so I'm going to have to round that to 4.7. Okay, so that's approximately 4.7. So it doesn't come out evenly, okay? And so, but I can still do it. It's just a little more tedious here. So it'll be x minus 4.7 squared all over 6 minus 1. Take the square root. Okay, so whatever I get for the top there, divided by 5, and then I take the square root. And so now I make my table, and I got 9, 3, 5, 1, 6, 4. This is going to be x minus x bar. This will be x minus x bar quantity squared. So 9 minus 4.7, that's actually going to be 4.3. And then 3 minus that, that's like a negative 1.7. So 5 minus 4.7, that's going to be like 0.3. 1 minus 4.7, that's a negative 3.7. 6 minus 4.7, that's going to be 1.3. And then 4 minus 4.7, that's going to be 0.7. Negative 0.7. Okay, so these are decimals now, so it's a little more tedious. And then notice I'm going to add these up, and you're going to see that these aren't going to necessarily cancel each other out exactly. What's going to happen is it's going to be close. Negative 3.7 plus 1.3 plus negative 0.7. So if I add these up, what I got here was negative 0.2. So what happened here is the reason this normally cancels out to 0 is that the mean is the balance point of the data set. It's actually where the data set balances. So the distances below cancel out the distances above. But in this case, this is rounded. I had to round the mean. So the 4.7 isn't the exact balance point of the data. And so it's not going to exactly cancel each other out, but you can see that it's close. It's near 0. It's not equal to 0. It's close to 0. And that's good enough, okay? But you won't get complete cancellation if you had to round the mean. So now I have to square each one of these. So 4.3 squared, this is like 18.49. Now you want to be careful. If I take negative 1.7 and I square it, I actually get negative 2.89. And the reason for that is it's going to do the exponent first and then take the opposite, because that's the order of operations. Exponents before subtraction. So if you don't want that here, then I'm going to do this. Put negative 1.7 inside parentheses and then square it. So this is going to take the opposite first, and then it'll square, so it'll take negative 1.7 times negative 1.7, and that'll be positive. Okay? So what I do is, either case, it's going to be the same number, so I just ignore the negative sign as I square. So like negative 3.7, I'm just going to say 3.7. And either way, I mean, I'm getting the right number, 13.69. 1.3 squared, 1.69.7 squared, 0.49. So you can see there's just a lot more work involved in doing the math here. So now I have to add all these up. Oops. 2.89, 0.09, oops, plus 13.69, 1.69, 0.49. And what I get here is 37.34. And so that is the sum that goes up into here, 37.34. And so now I can take 37.34 divided by 5. That would actually give me my variance. And then when I take the square root of that, I would get my standard deviation. And you can see that the standard deviation is 2.7. And that's the standard deviation. Okay? And so you can use the definition formula in the table to find the standard deviation. And that's fine. But it is going to be a lot more work. It's a little more tedious here. But there's another problem too, and that is that when you round the mean, you're actually rounding this at the beginning of the calculation. It's not like you're just rounding the very last number. You're rounding this at the beginning, and then you use it over and over again to find each deviation. So you get a little bit of error each time, then you square it, and so you know, when you have lots of values and you keep bringing in error, it can throw your results off. So it's really not the best method to use. Even though you could use it, you really probably don't want to use the definition formula to calculate the standard deviation. And so there's actually a different formula, and that formula is the computation formula for the standard deviation. Okay? And so let me first explain kind of all this formula is, how it works. And then in the next video, we'll actually use the computation formula to calculate the standard deviation for this data set. So basically what the mathematicians did here is they realized, okay, this mean here I had to round, and then I'm doing this sum over and over again. And so what they did is they took that sum, which is x minus x bar quantity squared, and they said, let's do some algebra on this. And so the x bar is the mean, right? So that would actually be x minus, the mean is the sum of x over n, quantity squared. And then what they did is if you remember in your algebra class where you FOIL, okay, you would take this times that. So, I mean, I can write it out. I'm not going to do all of it because you really don't need to do it yourself. But do you remember FOILing when you square a binomial? Then and this all is in the sum. And what they did is they did the first two, outer two, inner two, last two, combined like terms, and then they did a sum that had sums in it, and there's ways that you can manipulate this algebraically, okay? And then when they simplified it all, they got it to simplify to this: the sum of x squared minus the sum of x quantity squared over n. And this is the important thing here. This is all that you need to know here, is that this is equivalent to this. So this is an algebraic manipulation of this. Okay, now this is actually one of the calculations we did on the statistical sums worksheet. Okay, if you go back and, not worksheet, I don't know if you did a worksheet. You had a video on it. You did a daily activity. That's right, you had a quiz. But this, if you go back and look at that quiz, or you look at those videos, this is actually that final calculation. And this is why that calculation is so important, because it is an algebraic manipulation of this sum of squared deviations, which is actually a very important calculation in statistics. Okay, so really all that the definition formula is doing then is, when you're like at this point and you have like n minus 1 over this, is instead of using the table to find this, they're taking this and putting it into that circle, and they're getting the computation formula. I think I said the definitional formula earlier. I meant to say the computation formula. So basically the computation formula is just using this to plug in the circle, rather than this sum and the table that we did earlier to plug in the circle. That's really all the computation formula is. So now let me write it out officially here. The computation formula for the sample standard deviation is given by, so the computation formula for the sample standard deviation is given by the following. S is equal to, so on the top here you have this sum of x bar minus the sum of x quantity squared over n, and then all of that is over n minus 1, and then you take the square root of that. And that is the computation formula for the sample standard deviation. And then when you look at that, you'll notice there is no x bar in this formula. You simply have these sums that you plug in along with n to get the final answer. So there's really no rounding being done until the very end. Okay, so now in the next video we're going to use this computation formula to calculate the sample standard deviation for this data set.